For decades, the search for extraterrestrial life consisted of observing the sky in hopes of catching faint radio signals until an object called Tri-Atlas slowed down on its way to our solar system. Official data claims that its brightness can be explained by simple physical laws, but in just 4 weeks, its light increased 5 times more than expected. Meanwhile, spectrographs detected metallic traces that are usually created rather than found. And contrary to the well-known behavior of comets, this object barely deviates from its course, despite the visible gas emission. If the Tri-Atlas is a natural phenomenon, we cannot explain any of this. If not, perhaps we are witnessing the first interstellar visit under the control of an intelligent being. So what lies behind these impossible signals? For generations, radio telescopes scanned the sky in search of a single artificial signal, a beacon, a whisper, some coded invitation from another world. But in the silence, another channel opened up. From time to time, a solid body crosses the abyss between stars and enters our solar system. A macroscopic technosignature, if they exist, would look like this, not as a signal, but as an object. Since the beginning of modern astronomy, only 3 such visits have been confirmed. The odds are astonishing. For every 100 billion comets orbiting the sun, only 1 or 2 have come from another star. Each such arrival is a cosmic lottery ticket, a chance to catch something created, not born. The traditional search for extraterrestrial intelligence, focused on radio signals and lasers, assumes that civilizations are broadcasting. But what if the best evidence is physical objects, silent, inert, drifting in space? Objects can retain information, technologies, even intentions long after their creators have vanished. Unlike fleeting transmission, a macroscopic artifact can endure. It can be studied, measured, and, if lucky, intercepted. The rarity of these interstellar objects makes each discovery a global event. Oumuamua in 2017, Borisov in 2019, and now 3I/Tlas. Each of them is a unique opportunity, a probe from a time and place we may never see again. Their rarity means that even one anomaly holds significance. The universe offers few second chances. The original concept of searching for extraterrestrial intelligence was shaped by the tools of its time: radio telescopes, signal processing, and searching for patterns in noise. But the discovery of Oumuamua rewrote the rules of the game. Suddenly, the search for technosignatures began to include not only what we hear, but also what passes by. The Tri-Atlas is not just another comet. It is proof in motion, a messenger from another system. And perhaps, if we are attentive enough, a sign that we are not alone. On May 7, 2025, the TESS exoplanet observation satellite detected a faint, rapidly moving object against a dense field of stars near the galactic center. At that moment, there was no signal. The signal was buried in a digital sea of stellar debris. His movement was too subtle for automatic triggers, and his light was lost among thousands of background stars. For almost a month, the object moved along its path, captured night after night in test frame images, each adding another dim mark to the archive hard drives. Only on July 1st did the Saturn overview, conducted from the Chilean station in Rio Hurtado, record an anomaly. The brightness of the object sharply increased, growing 5 times since Tess first noticed it, yet its position remained in the densely populated bulge of the Milky Way, known for its ability to conceal temporal objects in plain sight. The small planet's center issued a warning, and within a day, observatories around the world switched their telescopes for further observations. In the following days, teams studied old data. The Zwicky Transient Facility in Pan-STARRS detected preliminary images from late June, showing the trail of an object moving steadily across the sky. Astronomy enthusiasts also joined the search, sifting through public archives, their findings filling the gaps from June 14th to the end of the month. Each new point on the timeline added details to the brightness curve, showing a burst of brightness that defied simple geometric explanation. The culprit was the sky itself. The approach of the object from the direction of Sagittarius meant that even the most sensitive observations struggled to separate its signal from the background. Only after the announcement in July did the entire picture of its early activity become clear through meticulous analysis of terabytes of archival data. For the testing and Atlas teams, the opening was not so much a sudden revelation as a slow process, ignited weeks before anyone realized that the interstellar guest had already arrived. From May 7th to June 3rd, Object 3I/Atlas increased its brightness 5-fold, which contradicts the usual patterns for distant comets. Standard geometry predicts only a modest increase, possibly 1.5 times brighter, when an object moves away from the Sun from 6.36 astronomical units to 5.46. Instead, The photometric data from the tests, ZTF and ATLAS, show a steady and constant brightness spike 5 times over a distance of nearly 0.9 of an astronomical unit. Data from each review is consistent, verified against field stars and synthetic solar analogs, with a systematic error below 1/10 of a magnitude. This is not a transient outburst or an instrument anomaly. The brightness curve, reconstructed from night stacks and tracked exposures, draws a clear arc, smoothly rising even as the object crosses a dense galactic cluster. At a distance of 6.36 astronomical units, no activity is expected. The icy water remains frozen. The warmth of the sun feels like a distant memory. However, the coma is already visible, and the measurements of the cross-section of dust increase from 300 square kilometers in May to more than 1,700 in July. These data withstand scrutiny, with arabesques sufficient to exclude random scattering or confusion with the background as a cause. Summarizing the flows, the odds sharply depart from mere geometry. Excessive light demands an explanation that corresponds to both time and scale. No survey, no matter how deep, can reflect the magnitude of the changes taking place. The displayed data leaves no room for doubt. The Object 3 I/Atlas had already shown activity and stood out against others before it was recorded officially. The search for answers begins with numbers. A fivefold increase in brightness, exceeding all geometric forecasts, requires more careful data analysis. Astronomers check familiar versions, instrument errors, confusion with the background, a fortunate line of sight through a galactic bump. Each of these hypotheses is tested, revised, and ultimately found insufficient. The light curve is consistently recorded across all telescopes and continents. Its smoothness is too great to be random, and it is too early for classical cometry activity. Some speculate that the true speed of the approaching object may have been underestimated, hidden among the dense star fields of Sagittarius. Yet even after adjustments for load and recalibration of photometry, the excess light flow remains. The numbers simply do not add up in a natural slow burn. This opens the door for bold ideas. Could 3 I/Atlas activate the engines by applying a controlled braking maneuver to match the speeds of the solar system? This is a hypothesis on the edge, but the timeframes match the data. A control slowdown performed far from the sun could explain the early and constant increase in brightness without the need for water ice or familiar volatile substances. If this is so, the object's activity will become a sign of intention rather than chance. However, with each speculative step, the need for caution arises. The sky is known to deceive even the most attentive observers, and the burden of proof is great. As the debates progress, attention shifts to the chemistry of the coma, where the next clue may be hidden in plain sight. VLT spectrographs, tuned to the faintest whispers of atomic light, have captured a mystery in the coma of 3 I/Atlas. Nickel lines, clean and well resolved, stood out against the background, while the iron that was supposed to be paired was nowhere to be found. The team at Paranel spent nights rechecking calibrations, making corrections, and matching laboratory wavelengths. The answer was confirmed. There was nickel, but no iron. In the solar system, no comet had shown such a ratio. In most cases, iron and nickel moved together, formed in supernovae and the cores of planetesimals. In the solar photosphere, there are about 18 iron atoms for every nickel atom. Even among the dustiest and most metal-rich comets, nickel rarely exceeds iron by more than twice. Here, the ratio exceeds 15, possibly even 50, with the iron lines hidden beyond the detection limit. A group led by Dr. Sofia Cardenas created transition maps of nickel-iron in both moderate and high resolution. The production rates fluctuated around 4.6 grams of nickel per second at a distance of 2.85 astronomical units, with reliable upper limits on iron pushing the nickel-iron ratio off the charts. Every attempt to uncover the hidden iron signals, accumulated data, attempts to reveal barely noticeable combinations yielded no results. Natural mechanisms struggle to explain what is happening. Thermal decomposition of nickel carbonyl, a fragile molecule that evaporates at low temperatures, may contribute to the release of nickel, but the formation or survival of iron carbonate is less likely. Some theorists point to selective dispersion or exotic fractionation during the formation of planetesimals. Others, more boldly, raise the question of engineering remnants. Nickel-containing superalloys worn by ancient engines have left their mark in the coma. However, the spectrum does not yet show fuel lines. No obvious signs of fuel or alloy. Only nickel, solitary, and the silence of iron. the elementary balance is disturbed, and the search for a natural explanation continues. By any standards, the trajectory of the 3I/Atlas is a paradox. Astrometric data from July to August show a drift of only 1 to 1.5 kilometers per day, a nearly imperceptible change, despite the coma and tails stretching hundreds of thousands of kilometers behind. For comets in the solar system, exhaust gases act like a rocket. Streams of vapor deflect the core from its course, creating measurable non-gravitational acceleration. But here, the numbers barely change. The path seems almost purely gravitational, as if the object is an inert stone rather than an active comet emitting gas and dust. If all the data is combined, the suppression of this rocket effect becomes obvious. Borisov, the last interstellar guest with a strong coma, drifted about 100 kilometers a day, almost 2 orders of magnitude higher. Even a modest tail should slightly shift the core, but the 3I/Atlas resists. Anti-tail, dust, visible streams. All this is seen in the images, but the orbit stubbornly remains unchanged. Models that take into account the observed mass loss and surface area predict a much greater shift in trajectory. The numbers refuse to cooperate. If the object were a mountain of ice and stone, the only way to completely suppress this effect would be a colossal mass, something so dense and enormous that even the strongest currents could barely move it. However, photometry and brightness profiles impose strict limitations on the size of the core. It is large, but not excessively so. The alternative is control, active stabilization, continuous correction, or a shell that absorbs or redirects the thrust. No natural mechanism can fully explain the gap between what we see and what we measure. Each astrometric update narrows the errors. The drift remains fixed just above a kilometer per day, significantly below the threshold expected by comet physics. The numbers are clear. 3I/Atlas moves through the solar system as if impervious to its own activity. The contradiction is mechanical, not just mathematical. In the world of natural objects, movement obeys mass and force. Here, the rules are distorted, and the path barely trembles. Against the backdrop of interstellar visitors, Borisov is a classic example. Its coma and tail, rich in cyanide and diatomaceous carbon, described a classic arc through the inner solar system. The readings matched expectations. The non-gravitational acceleration was about 10 to the -6th astronomical units per day, translating to a drift of nearly 100 kilometers per day. Each steam plume pushed the core, each eruption reflected in the orbit. Borisov behaved like a comet, obeying the physical laws of mass loss and solar heating. In contrast, Oumuamua ignored all customary rules. No visible emissions, no dust, no coma. Nevertheless, its trajectory sharply deviated near perihelion, with a non-gravitational acceleration of about 2.5 times 10 to the -4th astronomical units per day. This is 37,000 kilometers of drift, all without a single emission or tail. Its rotation, a stable 3 turns a day, only complicated the mystery. The models failed. Too little mass for a snowball, too much movement for a stone. Now the calculations involve an object 3/Atlas, but in the opposite direction. The coma is undeniable. The tail stretches for hundreds of thousands of kilometers, but the measured drift is barely noticeable. Only 1 to 1.5 kilometers a day. This is 100 times less than Borisov's, and only a fraction of Oumuamua's. The rocket effect is absent where it should dominate, and present where it should be unnoticed. 3 objects, 3 patterns, none fitting a single template. It seems the universe deals its wild cards in pairs of opposites. Rubin's observatory is ready at Karapacho. Her mirror, 8.4 meters in diameter, is ready to embrace the southern sky every few nights. With the inherited view of space and time, Rubin opens a new era of early warning. His rhythm and sensitivity mean that the next interstellar visitor, whether a comet or something stranger, will not escape notice in the crowded star field. Notifications will be sent in real time, giving professionals and enthusiasts the opportunity to act proactively, but telescopes alone are not enough to capture all the twists. The last 2 interstellar objects confirm this. When 3 pierce a galactic projection, it is the astronomy enthusiasts who sift through terabytes of archival data, creating the first clear light curve. A network of citizen scientists, armed with homemade telescopes and open-source software, fills the gaps between survey passes. Their rapid communication transforms scattered images into a timeline, capturing activities that might be lost in the noise. Now the stakes are raised. As the Atlas circles the sun, every night counts. coordinated campaigns, Rubin's night observations, a star conference in Hawaii, the Atlas in Chile, and amateur observatories from Pretoria to Perth unite into a global network. Each observer adds a new data point, reducing errors and refining models. The next eruption, the next spectral anomaly could occur at any moment. Early warnings spread through Discord servers and Telegram groups, prompting improvised follow-up observations with large and small telescopes. The call is simple. Look at the sky, monitor the brightness curve, explore the spectrum, share raw frames, and calibrate its stacks. In this new SETI, discovery is not just the privilege of professionals. Every warning, every image, every measurement brings us closer to capturing something incredible, a message written not on the radio, but in movement, chemistry, and light. Spectroscopic observations with a very large telescope reveal the presence of nickel in the coma, but the absence of iron, an unusual characteristic, while astrometric data indicate almost complete lack of non-gravitational acceleration despite visible ejections. In contrast, the comet designated 2 eyes and Borisov exhibit typical cometary motion, while the comet designated 1 eye and Oumuamua showed a significant trajectory change without any detectable outgassing. These opposing anomalies remain unexplained by modern models. There is no evidence of artificial control, but the physical contradictions in Atlas's behavior challenge accepted theories. Our best hints may come not as signals, but as objects whose movements contradict expectations.